Thanks everyone for coming to this. I know it's a little difficult waking up from the food coma after lunch. I was nervous about this slot, so I'll try to keep it interesting for all of you so you don't fall asleep. And if you do, don't be too obvious about it. Okay, so I'm Daniela. I am working in engineering at a startup in San Francisco called Lightstep. We sell monitoring software to other software companies, and our platform is primarily based on distributed tracing, hence the topic that I want to talk to all of you about today, focused on the insights that we can derive from trace aggregates. So I don't know the background for all of you in the audience, so I'm going to quickly go through a few slides on the basics of tracing, given that it's I think, a quickly growing concept. I'm not going to spend too much time on the basics and then move quickly into the theme for today, which is trace aggregates. So pictured here is our CEO, Ben Siegelman. He was the first person, I think, to come up with this terminology that I want to share with all of you today called the pipes of observability. You might have heard a different term called the 3 pillars of observability. People call them metrics, logs, and traces. The subtle difference here that I really want to share, because I agree a lot with it, is pillars sort of suggest that if you have either one of metrics, logs, or traces, you're done. You're good to go with your system after you are able to derive those metrics or logs or traces from your system. And that's false, because they're just data. Like, there's no value in raw data. The value really comes from what insight or what analysis we can present to developers so they understand the root cause or what's going on in their system. So the difference here is that they're really, you think of them as transportation for carrying the raw data to you. And then there's a step missing, which is the insight and the analysis, which sometimes humans do that manually. Here I'm going to present a bunch of analysis that I'm hoping machines can do for us because they don't sleep. Okay, so moving on, another quick review. There's a lot of talk about tracing today, so just want to quickly go through the value proposition. You've probably heard this elsewhere, so just bear with me for those of you that are familiar with this concept, which is traditional systems live on the same server or the same set of servers, and to scale, we just beef it up. We add more CPU memory, network, whatsoever, and it's all kept together in a monolith in one system. And the traditional monitoring tools give you log lines, metrics, counts, through that kind of window into observing into your system. But another buzzword I have up there, microservices break this paradigm, because for any given request, we now have hundreds, if not thousands, of smaller services serving a very small particular part of the functionality of your total system. And then you have this broken red line on the right where it might travel through a bunch of services, and if you still use traditional monitoring tools, you're going to get a log from server A, a log from server B, and you still have to thread either the logs or metrics together in order to tell the story. And a lot of the time it still happens manually, whether it's your on-call engineer or maybe a DevOps team. So the value proposition of distributed tracing is that a trace is the only piece of raw data that tells a story that's end-to-end in a distributed multi-tiered system, because it follows the request. It follows the the life of the request. Okay, so moving on, this is pretty crucial. So again, people probably have seen this before. I just want to make sure we're on the same page. Visually, in a lot of monitoring tools, any tools you find out there, if you Google tracing, will show a trace in a waterfall layout like this. So you have your top, what we call a root span. Each of these operations, each of these rows, we call a span, which is just a unit of work representing a part of a trace. So the root span, the yellow one at the top, is the one that you care about, the transaction that you're either trying to optimize or the one that serves your website or something that you want to monitor. And then calls out to different services. Each one I've highlighted in a separate color. Another web framework, several RPCs, maybe an even external call that you have to navigate some kind of network call. And then they might call out to other APIs. So then you get this nice waterfall. And then as you move from left to right, obviously, the length of the span itself represents the time that was spent in that operation. So that's pretty clear to everybody. Let's zoom out a little bit and look at a single trace without all of the details. You essentially, if you squint a little bit, see this waterfall view everywhere. If you look at a second trace for the same transaction, it has the same shape. Some operations might have taken longer and shorter, but generally has the same shape. Now the problem with tracing, well, not a problem, but one downside, you can't have everything, is that there's hundreds of thousands of transactions in a production system, and it's likely not feasible at all to capture all of them. And frankly, you don't want to capture all of them because you don't want to pay to capture uninteresting transactions. 99% of the transactions you probably don't even care about. So for tracing to be cost effective, it almost always involves sampling. Now you can be intelligent about the sampling, deciding where to keep, what traces to keep. For the most part, a lot of tracing systems, the basic ones, just do ingress sampling, meaning that you flip a coin or roll a die and you keep the transaction or not. So you have a set of traces, and in a lot of the tools, you will look at this tracing view, and this is what you see. And maybe you open it in 5 tabs, so you can look at like 5 different traces and try to find a pattern among them. Now the problem here is, of course, that humans have a limited capacity to analyze large amounts of data. So no matter how many Chrome browser tabs you open, you probably crash your Chrome before you're able to actually root cause and feel confident that you've looked at enough traces to know that the problem is caused by that exact one thing. If you're lucky, you might get a trace that tells you exactly what's wrong, but you don't know if the trace is representative. You don't know if you've captured an uninteresting trace versus the one that's causing your incident. So, of course, this is the meat of my talk today, which is what happens when we gather hundreds or thousands of traces and we feed it to a machine and we do all kinds of analysis and let the machine surface interesting insights to us so we don't have to do the manual analysis ourselves. So there's 3, I'm not gonna read through them all. I did want to highlight the last one because that's what my demo is gonna be on. Also, the first 2 have been more or less vetted by the industry and are in a lot of production system being used already. The third one is why I'm here today, which is to explore this concept of using it for a different kind of analysis. But I will go through the first 2 first. Okay, so starting with this concept of correlation based on statistical analysis. There's a lot of kind of fancy words there. I will go through what I mean. So this is a real incident that Lightstep suffered. I think someone got paged, and then we were looking at what happened a couple of days later to do a postmortem on it. And this was the dashboard that they saw at the time. So this is our internal dashboard. It's the first one that we go to. Clearly something went wrong around, I think, for those of you that can't see at the back, it's very small, but it's around 12 o'clock on Monday, the 22nd. There's a big spike in everything. Problem 1, when the on-call engineer came here, other than knowing that something was wrong because they got paged and that things are actually wrong in the system, very difficult to know which graph to dig into first because they're all correlated with each other. You don't know which one is just the symptom of the problem and which one is actually the problem itself. I'm going to skip all the investigation and skip right to the end. The root cause was that we had a customer that was inadvertently DDoSing our entire ingestion system. We should have had better protection against that, whatever, but that's a separate talk. Essentially they accidentally brought our ingestion system down. And then I had to manufacture this graph, which didn't exist on the dashboard, just to show that if you knew to segment by the customer ID, which we did have in some of the operations. And then I had to filter it down to all the different projects that the customer had. So I think they have maybe like 6 here. You could see that there was one project that was like obviously completely out of whack. We didn't have this graph. Now the problem is, I skipped the investigation. It took a few hours to actually get to the root cause and then contact them so they could, turn down. They had a faulty token, so they were DDoSing us because they had a really aggressive retry system. Anyway, it took hours and it just took way too long to get to such a simple root cause because we didn't know that we had to segment by customer ID. That is not something we have by default on our default dashboard page. And the reason why we don't have it is because we don't have that tag, because the cardinality, the number of unique values is too high. You can easily have hundreds of thousands of customers if you're like an Amazon. And it's just it's really expensive and infeasible to have these kinds of dashboards. We didn't have prior knowledge that we had to segment it by customers. And really, even if we did and we could graph it, it kind of looks like this. Well, it's most likely to just look like noise because the real signal gets drowned out by the noise. So that's sort of what I want to convince you all that is not efficient to do this kind of analysis with high cardinality values characteristics in your system using just metrics alone. So then I want to present how we can do this using tracing instead. So I've made this very pretty graph in Excel with my front-end skills. So the idea here is to use a different kind of analysis. Here I have a latency histogram. For those of you that's not familiar with it, because I wasn't familiar with it, we essentially create these arbitrary buckets for latency. So at the very left, you have 0 to 50. At the very right, it's between 950 and 1,000, and with some unit, let's say milliseconds. Oh, I actually put it up there. OK, good for me. So what we do is, let's say there's 1,000 traces we've collected for a given transaction. And we basically plot the count for each bucket. So if you have a transaction that's 40 milliseconds, we would increment the count of the leftmost bucket by 1. And we do this for all 1,000 of them, and we have this pretty latency histogram that represents all the latencies in your system for a given number of traces. I'm using 1,000 so that the math is easier, but it's obviously not that nice in reality. And then I've drawn a line for the P99 just to show you, like, I mean, this is literally how the percentiles are calculated. Is how to the right of the P99 line, we have the 3 buckets that contain the top 1% slowest transactions. And then you can see that as you move from left to right, the transactions get slower. OK, so what can we do now that we've plotted this? So remember that trace with the waterfall view, and then you have spans. So trace is a context-rich primitive, meaning that at the time of instrumentation, at the time when you generate the trace, you can attach tags. And these are not limited in cardinality. You can attach tags that have a lot of hundreds of thousands, millions of unique values, if you will. So one of the tags we can attach to this trace is which customer made this request. And we have these tags on all of our traces. And then given that, we have a bunch of traces, and you can look at, now you can run this statistical analysis. It's very simple. It's basically a correlation coefficient. So you look at the slowest, top 1% slowest requests, and you say, what are the defining characteristics? What's similar about these requests compared to the rest of the 99%? And then you can plot it again. So here I've overlaid a certain tag. So in this case, it was the problematic customer. And you can see there's a pretty strong correlation between requests that contain that customer ID and slowness of the request. And you can do this not just for this tag, but for any tag that has a high correlation coefficient. And it immediately reduces the investigation time from hours to minutes. It doesn't solve the problem. It's still a correlation, not a causation. But it is a very strong hypothesis for the developer to then now manually go check and look into whether there's actually something wrong with this customer, or maybe they just generate requests with a lot of RPCs associated with it. Maybe they just have giant requests. That's fine, but it's a pretty strong educated guess towards it. It's a hint to point an on-call engineer. If you get woken up at 3 a.m., your brain's really not working that well. And this page will basically tell you, hey, go look at this customer, see what's wrong with them. OK, so we productionized this, and it's pretty cool because that was a theoretical example. This is a real-world example that happened to one of our initial customers. So there was actually a faulty network card in one of their data centers. It's funny because in this case, it was a physical infrastructure problem that we debugged using software. And this is the latency histogram that they saw. And what happened was, I think there was this server rack. I feel like I'm way out of my league here. And something was wrong with the rack. And any request that happened to land on that server was just timeout. So you basically have this long tail latency. You have a cluster of transactions that for some reason took almost 100 milliseconds, where most of the transactions usually takes around 10 milliseconds. So they're investigating this. They pull up this histogram for all the traces they have for the transaction. And we draw the P99.9. So in this case, everything to the right of that line is in your top slowest 0.1%. And then in the black, we've essentially overlaid the correlation, the strong correlation we found, which is almost a perfect correlation between your top slow 0.1% and the server ID that they have. So using this, again, as a hint, so it still required somebody, I think maybe a technician, to actually go into that data center and then do a bunch of inspections to make sure that all the servers are up and running correctly and find the actual physical infrastructure issue, replace the network card or whatever, and bring the latency back to normal. And this took, and I don't want to quote them, but essentially it took a lot less time than it would have otherwise if ever they were going to solve this issue of long tail latency. So I thought that was a pretty cool example. Okay, finally, I want to now present something that we haven't productionized, and it's sort of an exploratory research into a new kind of analysis we can do, and that is on critical path. So back to this trace, we can, again, look at a couple of them. For the same transaction, it'll have a similar shape, and the similarity between all three of these traces is that red line I've highlighted to sort of draw everyone's attention to it. That's your critical path. We kind of define it as the operation that contributes to your overall transaction duration in such a way that if you reduce your critical path, you reduce the overall duration of your transaction. So that is what you want to optimize. You don't want to optimize one of those little gray bars. And actually, in reality, that's not easy to immediately figure out without looking at a trace or a bunch of logs or metrics to get that intuition. Anyway, so we've identified the critical path. That's actually the easy part. Rarely will developers be surprised when you tell them what their critical path is, because they know, it's probably some kind of a contention on a database or some kind of a third-party API call that just usually takes a really long time. So the where is not surprising, and it's valuable, but it's not that valuable. But rarely do they tell you, does any kind of analysis tell you why it's being contended upon. Sometimes you know when the system is small. As your system grows, you really don't know how the contention has changed over time. So the why usually lies, and this is a hypothesis again, usually lies in the fact that all latency issues are due to contention of some sort. So contending upon CPU, memory, network, a database row. My example today here I've picked in particular is a lock contention, a mutex contention, which happens, I think, a lot, even internally in our system. We have this all the time. So in this case, I've put the word mutex acquired to show that the critical path is you've come up to this point in your operation, you want to acquire a lock to do the work. It's not available, so you wait for it. And that waiting period is your critical path, and then you can see that little gray bar at the end when you finally acquire the lock and do a little bit of work and then release it. So that's what we're going to look at today, pretend that there's a lock contention in some kind of a system. Really, the analogy that I really like to think about is understanding why traffic is jammed. So in a traffic jam, if you're in one of those cars at the very end, you want to know what's going on and what's holding up all that traffic. And it's actually pretty difficult to figure it out without being there yourself. Sometimes there's like various stupid reasons, and maybe you could have gone around the whole traffic thing. Maybe everybody is trying to take one exit and you don't even want to go to that exit, but you're not sure because you might miss out on the exit. So essentially, if you knew what was going on, you can make a more intelligent decision about where to go next and how to optimize your journey. And that's exactly what we're trying to do here. We're trying to figure out what's going on with the lock so that we can figure out how to optimize it further. So we're not doing work and taking stabs in the dark, hoping that it'll help with the situation. So thankfully, with that analogy, we can use trace aggregate analysis, again, to sort of stick with the theme of today's talk. How we do that is, I basically overlaid a bunch of traces here to illustrate what this analysis is doing. I've removed, however, all the other spans except for the critical path. So at the bottom with all the colorful bars, those are all the critical path of all the different traces that you've collected. And they're various length, but they're always the critical path of their particular trace. And what you can do with this, remember there's this concept of tagging each of your trace. You can tag your trace with the lock that is trying to, that is being acquired, right? So you can uniquely identify each of your lock in your system by just an ID. And then you can figure out, you can gather the critical path, group it by the lock ID. So you're studying a particular lock. In this example, you're studying some lock ID mutex F7, 8, whatever. And then you can look at all the callers. Remember, in the trace, it's context rich, so you can actually backtrace and backpropagate and figure out who's actually trying to call to acquire this lock. And then you can aggregate by the callers. Then all of a sudden, if we present it nicely and visually, you get a very clear picture of what's contending for resources in your lock and which resources are contended by which callers upstream, right? And this could be several layers up. So you can go as far up as you want in order to get that kind of insight. So this is what I'm going to try to do in my example today. Before I go into the demo, I did want to cover two very simple terminologies because I'm going to use it later. Is this concept of having waiters, so these are the processes, the threads or whatever. In my case, it's essentially different like orders. You're going to see what I mean. And they're called waiters when they're waiting on a given lock. And then after they acquire the lock, they become holders. They hold on to the lock, do the work, release it for the next person. So the architecture that I've set up today, it's, you know, a little fun startup that I have, Donut as a service. Move fast and bake things. So it's a really simple web app I wrote in Go. It has a donut client that orders donuts on the background. It generates all these orders for different flavors of donut. And then I have a donut server that serves these orders, sends them to the payment service, make sure that they're paying me for my service, and then go through the fryer service and the topper service. Both of these are serial. So you can only fry one donut at a time, so you must acquire the fryer lock before you can fry your donut. And then move on to the topper service. You must get the topper lock and then sprinkle your donut before giving it to the next donut to be sprinkled, or sorry, to be topped. And then in my example, what I've also done is I have a little donut generator running to order these donuts. I've basically varied the rate of the amount of orders that's been coming in. That'll be really obvious when I do my demo later. So you don't have an equal amount of sprinkles donuts versus chocolate versus cinnamon. Okay, so I've tried to procrastinate this, but here we go. So what I've done is I will switch to my handy terminal window and start my generator. So I have the program running in the background, and then maximize this and go to my program. There we go. So I have a little demo project set up to receive the traces from the donut application that's running. And then I'm gonna go find one of the traces just to show you what I mean. Sorry, it's a little slow. The computer's running pretty hot. And I'm gonna go to the donut web server. So this is a little search interface that I can find traces easily. And then I'm going to go to my background order, which I talked about. And then I'm gonna run my query. Give it a second to gather all the information. By the way, you can see this histogram. It's literally the screenshot I took earlier. Okay, so we have a list. You can see they're all taking like various number of seconds. I'm just gonna open a random one in a different tab to show you this trace. It's the same trace of that architecture, but represented in that waterfall format that all of you now are so familiar with. Let it gather, assemble. Cool. So as you can see, because we don't know how long the transaction if it's done or not, we're just waiting for it to finish assembling, but it's pretty much done. As you can see, this is your root span, the background order. I've actually tagged it with a flavor, cinnamon. And then it goes into making the donut. We can collapse it just to focus one span at a time. The make donut operation then has 3 sub-operations: process, payment, fry, and then top. So if we open fry, we can see that there's a fry donut operation. Again, you can see that cinnamon, the tag is sort of threaded through. And then it goes into mutex acquire. So this is your critical path. In our UI, we actually highlight it in yellow to show you that this is the critical path that is waiting for the fryer lock. And then if you come down here to mutex hold, you can see that I've tagged it with fryer lock, so that later on when I do my analysis, I know which lock I'm looking at, fryer versus topper. In your real system, obviously, you're gonna have way more locks than 2. And then the exact same setup on the sprinkle side. You have the flavor tagged, and then if you look at the lock, you can see that it has a different name called topper lock. So this is the trace, essentially as expected. And then what I basically have here is, let me maximize this. I have added this little analysis that now I run on the back end. Now I am essentially a back-end engineer, so this is the prettiest visualization I could come up with on the front end, but you can imagine the possibilities here. So I did a little, graph. I picked out the two locks. The top is, let's say it's a sprinkle here. So the top is the topper lock, or the lock you have to acquire to put your topping on. The bottom is the fryer lock. The difference in them isn't that interesting, so I'm just gonna focus on the top one. And over here, what you have is the waiting time, right? So if you look at the waiting time, the dark brown is sprinkles, is chocolate. Of course, dark brown, yeah, I did that. The reddish one is cinnamon, and then the green one is sprinkles. So the different colored bars show you the different flavors on how long an order for that donut has spent in total time, right? So this is like total whatever wall clock time that they spent waiting for that lock to be available. And you can see that like cinnamon just towers over everything else, which makes sense because when I generated my background order, that's the sort of the rate that I turned up the rate for cinnamon. Waiting time is actually on average pretty fair, so you can see that the Go lock library works, so that's good. It's essentially a random selection. Now on the holders, it's pretty interesting now because you can see it takes so much longer to apply topping for a chocolate donut. And that's, again, sort of by design. I put in a little a timer for how long each topping takes, and chocolate does take a longer. But if I hadn't, if that was just the real system, then I don't know that. But it's very obvious, right? If you look at these two graphs, to actually gather this data one by one and look at a trace, maybe you would have gathered that, like if you look at enough traces with a chocolate order versus the cinnamon order, you figure out like, hey, it's holding onto the lock a lot more. But I just think that it's very difficult to say with how much confidence that happens. And this basically gives you that data. You can show somebody this and say, look, chocolate holds onto the lock for way longer. And a simple solve in this case, what we would do is break out the lock. Like chocolate can have its own lock. It can hold on to the lock for as long as it wants. It'll still impact other chocolate orders, but that's sort of a bigger architecture redesign. And then cinnamon and sprinkles can still share the same lock. And you know what? It'll make your cinnamon order so much faster and increase the throughput of your system and whatever, make more money. Maybe we can raise a different round of funding with this kind of analysis. So I don't know, I thought when I did this exercise it was pretty cool. So back to my presentation, because I want to respect the next, can't find it. There we go. Oh, that worked, look. Oh, and then I don't need my backup slides. Cool, so I just, just in case, it always happens. Thank you, yeah. I'm a very strong believer in Murphy law, by the way. I even have a video on my desktop if like everything else fails and the slides like disappear or something, which it almost did. Okay, so what was this talk about? I need to wrap up now so that the next speaker has time, and hopefully we have time for some questions. This talk was about a list of things. I said a lot of words. And I usually get a lot of advice for public speaking from people who are much better at it than me. And I've heard this advice many times, which is that you always talk about what you will talk about at the beginning of your talk, and then you repeat what you talked about at the end of your talk. I'm not going to do that today. I don't want to do it because I never remember these things when I'm sort of an audience. So I just want you to remember that trace aggregates is what you want, not just the single trace. You're not done if like a fellow developer comes to you and says, like, look at this trace, and you're going to be like, okay, where is your analysis? Where is your aggregate analysis? Because I truly believe that the time of getting a single trace is over. Like, maybe 5-6 years ago when tracing was still a pretty new concept, it's exciting to see a trace, but it's only one transaction out of millions, and it's not representative, and it's just hard to really do anything with a trace. So please remember trace aggregates, just those two words. I feel like everybody can do that. And then before I end, just a quick plug for OpenTelemetry, which is something that our company contributes a lot to. I'm really excited about it. It's essentially the next major version, if you've heard about open tracing and open census. It is the open source standard for telemetry data. Logs, metrics, tracing primarily. I think I'm obviously we work with the tracing aspect of it a lot more. In order to get any kind of insight, you need at least I think, thousands of traces. So in order to get aggregates, you need a lot of traces. In order to have a lot of traces, you need to figure out how to get those out of your system, instrumentation, integration with existing libraries that have them. And you probably don't want to be locked into a given vendor. So open source is good. That's why I'm excited about it. And it's also super exciting that this is potentially sort of the native built-in feature for any cloud-native integration or cloud-native software. So if you use Kubernetes, if you have a service mesh and you use Istio, it's it'll eventually be built in. That's super cool, and you get telemetry data for free, in quotes. Cool. I think I stuck to my timeline. Thank you very much for listening. I should have questions. Let me just double check the time. 5 minutes for questions. Perfect. Do we have any? Yes, sir.
So with open tracing and open telemetry, how did you learn about how to put useful traces in?
Yeah, repeating the question, with open telemetry or any of the open tracing, open census, how do you know how to put useful traces in? Really good question. You're the developer. So there's two ways, right? There's manual instrumentation and there's automatic integration, which I kind of alluded to a little bit. If you're using a third-party library that's really popular, I mentioned Istio for service mesh, they already have that built in, and all you have to do is sort of configure like a few lines of configuration to tell them where to send your traces, and voila, you have everything. If you want more in-depth instrumentation of your actual application logic, then you're the one that wrote the program. You're the one that should know which pieces are more interesting. There's a lot of best practice blog posts, videos, talks on how to construct your trace and how to optimize sending traces so that you're not bombarding your tracing vendor with too much uninteresting traffic. So that's how you would have to learn to figure that out in your system. And again, there's best practices around like which functions like you don't want to trace per for loop, for example, per iteration of your for loop. So these things, the literature is out there. Anything else? Feel free. I'm going to stick around, probably around this area, if you want to come up and chat about other things if you don't feel comfortable asking a question in public or it's too in-depth for a public forum. Otherwise, I'm going to let the next speaker have time to set up. Awesome. Thank you.